Okay, in this video we're going to be doing Calc BC Problem Set number 18. The problems and a playlist are in the description below. Let's take a look. Number 1, we want to find the interval of convergence of the sum from 1 to infinity, 3 to the n plus 2, quantity x plus 1 to the n over n cubed 2n plus 1. I ran out of steam while I was reading that. Alright, so we're going to use a ratio test on this. That's going to be the limit as n approaches infinity of the absolute value, which I'm putting in even though this thing is always positive at this point. Actually, it's not. Sorry. There's an x in there, right? An x could be anything. So we do need to include the absolute value for sure. It's going to be n plus first term. So we're going to get 3 to the n plus 1 plus 2 is n plus 3. You get x plus 1 to the n plus 1. You're going to get n plus 1 cubed. And then you're going to get 2 times n plus 1 is 2n plus 2 plus 1, so 2n plus 3. And then times the reciprocal of the original, so n cubed 2n plus 1 over 3 to the n plus 2, quantity x plus 1 to the n. Okay, so now we got to do some algebraic stuff, which is the stuff that makes this my favorite thing to do. Look at the 3's. We got 3 to the, so I mean, it's still a limit, but we got 3 to the n plus 3. Actually, I'm not going to take the limit. I'm going to do the limit in my head. 3 to the n plus 3 over 3 to the n plus 2. Just leaves you with 3 to the first 3. You have x plus 1 to the n plus 1 over x plus 1 to the n. Those are going to cancel down to just the absolute value of x plus 1 because you still have the potential for x to be positive or negative. Got to have the absolute value there. Now look at what's left. You have 2n plus 1 over 2n plus 3. You have n cubed over n plus 1 cubed. Those are the same degree, same coefficient. So when you go to infinity, those ratios will just go to 1. So both this one for n plus 1 cubed and n cubed goes to 1. 2n plus 1 over 2n plus 3 also goes to 1. They're not contributing anything. So all we're left with when we take the limit is 3 times the absolute value of x plus 1. That's all the work you really need to show for this. This needs to be less than 1 for the series to converge by the ratio test. So we definitely know that the absolute value of x plus 1 has to be less than 1/3. So if the question was find the radius, we'd be done. The radius is 1/3. I don't know which one they ask more often. I mean, the radius is obviously slightly easier to find because now we actually have to work out the interval. So this thing is centered at -1. So I'm going to draw a number line and put -1 in the center. And then I can go 1/3 in either direction. That's like the point of the radius. So the ratio test is inconclusive at endpoints, right? So we don't actually know what's happening at the endpoints yet because we've only used the ratio test so far. So this is -2/3. This is -4/3. We have to test them, right? And so to test them, you just take the value and plug it in. So if I take -4/3 and plug it into the original, I end up with something that looks like this. 3 to the n plus 2. And then it's -4/3 plus 1 is -1/3 to the n, and then all the n stuff just stays, right? So what's important here is we have 3 to the n times 3 to the second, which is 3 to the n plus 2. So 3 to the n times 3 to the second, -1/3 to the n. So 3 to the n, -1/3 to the n is just 3 times -1/3, -1 to the n. So we have our sum. We have -1 to the n, 3 squared, which isn't really doing much. And we still have this stuff. So this is an alternating series where the terms decrease in magnitude and have a limit of 0. This converges by the alternating series test. That will happen a lot. You use the alternating series test a ton, and then you'll get like p series and geometric series frequently as well. Let's test the other endpoint. So we have x is -2/3. Go up, sub in your -2/3. Just get 1/3 to the n this time. So this one is a little bit different, right? It's 3 to the n, 3 squared, 1/3 to the n. 3 times 1/3 is 1. So 1 to the n is just 1. So all we have here is 3 squared over n cubed, quantity 2n plus 1. So this is definitely convergent. We can limit compare it to the p series, 1 over n to the 4th. You can basically look at it and know that converges, but you do usually have to give a reason. So limit comparison to the convergent series 1 over n to the 4th. So our interval of convergence will contain the endpoints. And so it's -4/3, less than or equal to x, less than or equal to -1/3. There you go. All right, that's question number 1. Let's take a look at question number 2. Function g of x is the inverse of f of x. That is g of x equals f inverse of x. Use the table of values for the differentiable function f of x and its derivative f prime to answer the questions that follow. All right. Approximate f prime of 7. That we're just going to find where does 7 fall in the table and use the average rate of change. So f prime of 7 is approximately, it's a big deal that you write approximately there. 7 is between 6 and 8, so we're going to do f of 8 minus f of 6 over 8 minus 6. So that's going to give us, kind of confusingly for me, 6 minus 8 over 8 minus 6, which is just negative 1. That's our answer. Don't overthink it. Part B. Write the equation of the line tangent to g of x at x equals 8. This is another one. Don't overthink it. Just know what you're doing and get it done, right? So this x equals 8 is for g of x, which means it's a y value for f of x. So find that in the table, which means we're dealing with the point 6, 8 on f of x. So the ordered pair on g of x is going to be 8, 6. I always like to write all this down so that I don't screw it up. The slope of f of x, so f prime of 6, is negative 4 from the table again, which means that g prime of 8 is 1 over negative 4. And now we have all the information that we need. Our tangent line for g, I use colors so that I could keep track of what goes with what. The number one thing that I see people screw up here is they actually mess up the ordered pair. Like they use the ordered pair from f of x when they write this. Don't make that mistake. It's easily avoidable. All right, next up. We want to show that f prime of c is equal to negative 1/2 for some c between 2 and 10. So this is definitely going to be the mean value theorem, I think. I mean, I guess technically it could be intermediate value theorem, except we don't know that f prime is differentiable, so we don't necessarily know that f prime is continuous. And also, it doesn't work. Like negative 1/2 is not in between any of those values in the table, so we can't use intermediate value theorem on it. So mean value theorem was my first thought, and it is actually how we're going to do it. To use that, we need to state that our function is differentiable it has to be continuous on the closed interval and differentiable on the open. But more often than not, I don't remember what I just said. It has to be continuous, closed, differentiable, open. I hope that's what I said. More often than not, you're just told the function is differentiable and therefore continuous. So in this case, that is what we were told. So f of x is differentiable, so f of x is continuous. Therefore, by mean value theorem, we just have to find an interval on which the average rate of change is negative 1/2. Fortunately for us, the very first interval, the x's change by 4, the y's change by negative 2, and negative 2 divided by 4 is negative 1/2. So there's our negative 2, there's our 4, we're good. So f prime of c is going to be equal to f of 6 minus f of 2 over 6 minus 2, which does just equal negative 1/2. And then for some c that's an element of 2 to 6, sometimes when I'm feeling like, like super precise, I'll then say, therefore, for some c between 2 and 10, 2 to 6 is definitely between 2 to 10. No one should be taking off points for that, but, you run into all types. All right, let's take a look at the next one. Number 3, let R be the region in the xy plane bounded by y equals x plus 2, y equals 1/2 x squared plus 3x minus 4. Find the volume of the solid having base R and cross sections perpendicular to the x-axis that are semicircles. Okay. We have to find where these things intersect and just like what they look like, right? So, I mean, one of them is a quadratic that opens up. One of them is a line. If they define a region, it must look basically like this. So that's how I kind of like do the work for that. So we need to know when x plus 2 is equal to 1/2 x squared plus 3x minus 4. I'm going to multiply everything I see by 2, which gives me 2x plus 4 equals x squared plus 6x minus 8. Move everything to one side, which gives me x squared plus 4x minus 12 equals 0. I'm going to factor this thing, so it's going to be x and x. And then we're going to go with plus 6 minus 2 to get 4 as our middle term. And so that means that the intersections occur at x equals negative 6 and x equals 2. So those will be the bounds of our integral. If we're doing semicircles, it's pi over 8, the integral of s squared, right? And s is just top take away bottom. So we are doing pi over 8, the integral from negative 6 to 2, and then top take away bottom. Since they don't have names and I don't feel like renaming them at this point, I'm just going to do the quantity. The top is x plus 2 minus quantity, the bottom. So it's going to be 1/2 x squared plus 3x minus 4. It's at this point that I realized there's no way I'm doing this by hand. So I just grabbed a calculator and had the calculator knock out the answer. You can do that too. There's no reason to do this kind of integral by hand, I don't think. But again, you run into all types. Somebody might make you do it. I'm not going to. This would definitely be a setup, but do not evaluate, or set up and use your calculator. I don't know. If it's set up and use your calculator, this is all the work that I'd probably want to see anyway. Although honestly, if it's calculator, why not just use the calculator for the intersections? I don't know. Back and forth on that. All right, next problem. All right. Find the volume of the solid having base R and cross sections perpendicular to the x-axis that have cross-sectional area A of x equals 1/8 x squared plus 1. Where I think that 8 looks a little weird, but there's nothing I can do about that. All right, so to find volume, you're just integrating the area of a cross-section, right? The reason there's a pi over 8 in front of the semicircles is because when you find the area of a cross-section, it's pi over 8 s squared. Here, it's just, for whatever reason, the formula worked out to 1/8 x squared plus 1. So to do this, we're really taking this region, again, we're going from -6 to 2 of just a of x dx. So that's this. I'm going to do this one by hand because this one isn't as bad, but it is still not great. All right, step 1, reverse the power rule. So we get 1/24 x cubed plus x. And we're going from -6 to 2. It's really like the -6 is the problem here. Fundamental theorem. So we're just going to plug in 2. We get 8/24 plus 2. And then minus the quantity. I'm just going to plug it in and think about it later. -6 cubed over 24 and then minus 6. All right. The first part here, we just have like 1/3 plus 2. So 1/3 plus 6/3 is 7/3. And now for the second part, if I have to do this by hand, what I do a lot of is just prime factorizations. It's easier to simplify fractions when you have prime factorizations, in my opinion. I mean, there's other ways to do it, probably better ways. But what I'm going to do is I'm going to say this is -2 cubed times 3 cubed over 2 cubed times 3, and then minus 6. You can see there, though, it's like easy to simplify that, in my opinion. 7/3 minus, you just have -9 minus 6, which is -15. So you have 7/3 plus 15, basically. So 7/3 plus 45/3, which is 52/3, which is the final answer. It's not going to get any better. All right, that's the entire problem set. I hope this was helpful, and good luck.